Now we're going to move on to E2 reactions. These elimination reactions use bases, not nucleophiles. And you want to remember that strong bases will be unstable. And how you determine whether something is stable or unstable is you want to use the atom, resonance, induction, and orbital. So we look at those four things to determine if the base is unstable. And we will need to use strong bases. Okay, so this is the mechanism. I'm going to change to green here. We have a base, and we have an alkyl halide. The base is going to come in and steal that hydrogen, or that proton, off the side. The electrons that were attaching the carbon to the hydrogen, and they're blue here, are going to go and make a pi bond. That would give this carbon 5 bonds, and that can't happen. So the electrons that attach the carbon to this halogen will have to go with it. And so what we'll get will be a carbon bound to a carbon. It's got, that was the structure that we had to start with. The pi bond is going to be made of these blue electrons that were here. They've just shifted here. The halogen will be over here by itself, and it will have the pink electrons with it, these electrons. And the base, I think I did it out of blue, is here. And it will have that proton on it. And so we've got 3 arrows, the 3 sets of electrons are moving. E2 elimination is concerted. It occurs all in one step. So all of this happens at one time in a kind of a cascade. It's bimolecular, and its rate is dependent both on the alkyl halide concentration and on the base concentration. So I'm sorry, I forgot to put the K in the front. There we go. That's the kinetics. And so what would happen in this reaction, what would happen if we triple the amount of chlorocyclopentane? Well, we would triple the rate. If we don't change the concentration of chlorocyclopentane and we double the sodium hydroxide, we will double the rate. If we double the chlorocyclopentane and we triple the sodium hydroxide, we get a rate that is 6 times as high. So we looked at kinetics with the SN2 reactions, and then we looked at the substrate. And we found that with the SN2 reactions, substitution, the nucleophile could not get into this carbon if there were lots of bulky groups around it. This is a tertiary substrate. This carbon is attached to 3 different groups and a leaving group, which is our halogen. And this nucleophile cannot get into the middle, and so a tertiary substrate is too sterically hindered, and the nucleophile cannot penetrate and attack. However, the base is able to pull off one of the hydrogens. This is the carbon that's in the middle. It's got 3 bulky groups around it and a halogen. But when the base comes in, it's not trying to attack this carbon here in the middle. It's just plucking a hydrogen off the outside. And so that beta proton is able to be extracted even though the substrate is tertiary. So tertiary substrates undergo E2 reactions rapidly. They don't have the steric hindrance that the other one has, that the SN2 has.